Yeah, sure. Go and make a series about evolution. And don't even define what evolution is in the first episode. Ramble on and on about speciation and genetic barriers without even explaining the process that makes it all possible. Fewer people probably really know what evolution is than what a species is. Uh, well, anyway, welcome to episode 2. It's actually about evolution this time, and probably should have been episode 1. Though, given the view count on the last episode, I probably shouldn't even be making an episode 2. But here we go. Today, we are going back to basics. So, does anyone actually know what evolution is? It's when a species gets bigger, better, and stronger, right?
Wrong.
Don't worry. I'm not going to do the same bit as last episode. I'm just going to tell you outright this time. However, before I do that, let me set some ground rules and clear up some common misconceptions. It's important to understand that individuals do not evolve. Populations do. Individuals may change and grow over the course of their lives, but this is not evolution. In the most extreme cases of a change in body plan, it's a metamorphosis. Pokemon is not an accurate depiction of evolution, and in a few cases, it's more of an atrocity than a form change.
Look how they massacred my boy.
And whatever is happening in Digimon is also definitely not evolution. I don't think this has ever been observed in nature. Man, this shit is still so hyped though. What was I talking about? Oh, right. Animals don't just manifest rocket thrusters through the power of friendship. Another important point to elucidate is that evolution does not have an end goal. This is a blind process that is governed by several interacting factors based on the chemistry of inheritable genetic information. Sometimes these factors do shape an organism better suited to survival, but there is no predetermined design that the process is working towards. Besides, the results of guided evolution in fiction is almost always horrific. So, what actually is evolution?
Teacher, I know. It's when natural selection makes a species more fit for its environment.
Good job, Lucas. That would be an excellent answer if it wasn't incorrect. You see, many people use natural selection synonymously with evolution, but in actuality, natural selection is just one component of the much larger process that is evolution. That evolutionary process is defined as change in allele frequency in a population over time. That's what evolution actually is. Oh, I guess I should define what an allele is. And what their frequency is, right? In that case, I have another common misconception to clear up. See, most people use the word gene incorrectly. They'll say something like, I have the gene for brown eyes, or I have the gene for blonde hair, suggesting that we all have different genes from one another, and that those genes are independent. In reality, humans all have the same genes. It's one of the things that makes us the same species. What we do have is different alleles. Let's take a closer look. See, a gene is actually a region on your DNA. Since the human genome shares the same organization across all humans, we all have the same layout of DNA, and therefore have all the same regions. A specific region in the genome is known as a gene locus. My chromosome 1 contains the same regions as your chromosome 1. I'll go more in depth on this topic and explain it better in a future episode. For now, you only need to know the basics. So, this gene might be the region that determines eye color. We all have the gene for eye color. However, what may differ between individuals is what is present at this gene locus. The different information one may have at their gene locus for eye color may result in them having a different eye color. Sometimes it doesn't though. Like I said, I'll explain this complicated topic in more detail somewhere down the line. The different versions of the information that can be present at a particular gene locus are alleles. Alleles are essentially different versions of the same genes. Got all that? I know it's a lot to take in all at once. An easier way to think about it is that genes are like inventory slots in an RPG, and the allele is like the equipment that gets slotted in. We all have the same slots, but the loadout in those slots are different between individuals. This is a gross oversimplification, but I hope it helps you conceptualize what's going on here. That was a long aside, but it was necessary to understand the definition of evolution. See, these alleles are inheritable from parent to offspring. The frequency of an allele is the ratio of the population that carries that particular allele. The higher the ratio, the more common that allele is in the population, and the more common any traits dictated by that allele will be. A certain eye color, hair color, etc. The frequency of a particular allele increases when those carrying it have a greater number of offspring the following generation than those who do not have it. Conversely, the frequency of an allele decreases when those carrying it produce less offspring than others. The reason that an allele may increase or decrease in frequency can vary, but evolution is simply the change in those frequencies in the population over time.
Teacher, I know why the frequencies of alleles go up and down. It's because natural selection results in those more fit to survive passing their allele down at a higher frequency, right?
Just blurting your comments out again, huh, Lucas? Well, that's okay. Because you are correct this time, but only partially correct. While yes, natural selection does influence allele frequency in a population, it isn't actually the main driving factor in these changes over time. You may be surprised to learn that the vast majority of alleles are synonymous, meaning they have a different sequence from another allele, but end up containing no different information actually. Again, it's complicated. I will explain it in a future video. Like and subscribe! In the case with synonymous alleles, there are two or more different versions of the gene, but they all end up having the exact same outcome. How can natural selection result in the best allele becoming more frequent if they all do the same thing? Well, it can't. In this case, the frequency of these synonymous alleles are governed by almost entirely random chance, as the carriers of these genes are not mating any more or less based on these particular neutral alleles. This process is referred to as genetic drift, and is actually the most common form of evolution. Sure, it doesn't do much for the species, but these neutral alleles, meaning they don't help or hinder the organism carrying them, are fluctuating up and down in the population every generation. This is one of the ways that populations lose genetic diversity over time, in a process referred to as the drunkard's walk. This is an actual metaphor used by actual evolutionary biologists. In this example, a drunken reveler is plodding his way home after a New Year's Eve party. He is meandering his way down the road next to a railroad track, swaying back and forth as he walks. This reflects how a neutral allele can fluctuate up and down in frequency randomly in a population. The drunk man may sway back and forth for a while longer, but eventually he is going to fall and pass out to sleep off the booze. It's an inevitability. Two outcomes are possible. He tips over to the right, passing out on the tracks, and doesn't survive until morning. Or he tips to the left, safely falling into the snowbank on the side of the path and sleeping soundly until the morning. These are the two possible fates of a neutral allele. They can teeter back and forth for many generations, becoming more or less common in the population through random chance, but given enough time, they will either go to a frequency of 0, meaning no one is carrying it, completely removing it from the population. It has fallen onto the tracks. Or it can go to a frequency of 1, meaning that literally everyone in the population carries it. At that point, there is no other allele that exists to slot into that gene, and that one allele is the only option. It has safely fallen into the snow and will survive. An allele that is the only remaining option for a particular gene locus is said to have gone to fixation. Everyone in the population carries that one allele, and there is no variation for that particular gene anymore. This is one of the main ways that populations lose genetic diversity over time, becoming more genetically homogeneous. This process is even faster in small isolated populations. A cool aside, detecting these synonymous alleles that have gone to fixation is what is used by ethnicity test products like Ancestry. If a process like genetic drift is removing diversity from the population, where is new diversity coming from? One process that can inject some new alleles into a population is known as gene flow. If you recall our lowland gorilla harlots from the last episode, individuals do sometimes migrate to a new population, carrying outside alleles with them. If these alleles are neutral, they'll be subjected to the same genetic drift forces and have a chance to be lost or go to fixation in the new population over time. There is a case where an introduced allele is actually beneficial to the new population it's been injected into. This phenomenon is known as adaptive introgression and causes a newly introduced allele to shoot up to high frequencies in the new population over relatively few generations. This process actually occurred several times in the history of Homo sapiens, where modern humans would migrate into an area already colonized by other human species, such as Neanderthals or Denisovans. These species had been living in these areas much longer and had adapted to things such as the local food supply or local pathogens. So when alleles got passed around, Homo sapiens were essentially able to receive pre-adapted traits that helped them survive in the new environment. Alright, we've seen how alleles are lost by a population, and how some new alleles might be injected into a population to temporarily boost diversity. But the astute amongst you are probably already noticing an issue. If genetic drift and gene flow were the only two forces at play, slowly but surely all the genetic diversity would be lost, first within a population, and eventually even between populations. All groups of a given species would have the exact same allele at a given gene locus, and there would be no variation within the species anymore. Something must be creating new diversity to counteract the slow erosion of diversity by genetic drift. Well, that new diversity comes from mutations. Without going into the very complicated chemistry right now, mutations are mistakes during the copying of genetic information. Those mistakes cause there to be a new variation at a particular locus in the genome of the individual with the mutation. And what do we call it when one locus has multiple different versions? That's right, an allele. All alleles began their existence as a mutation in one individual. And if the mutation happens the right way, it can even be inherited. These inheritable mistakes are the sources of all genetic variation among all life on Earth. Of these new alleles that are created by this process, some are beneficial and give the organism an advantage over others. Some are detrimental and hinder or even kill the one carrying it. But the vast majority are completely neutral and make absolutely no difference at all. In fact, the average human has 10 unique mutations that occurred in their own genome, meaning they didn't inherit it from either parent. They are bespoke errors, just for you, that probably do nothing at all. That's right though, you and all life on Earth are actually mutants. It's just like the X-Men. Except without any of the cool powers. But with all the crippling depression. Anyway, You can pass these brand new alleles down to your descendants, where they will be exposed to all the other genetic forces we've discussed so far. Who knows? A neutral mutation that occurred in you may become an allele that eventually goes to a frequency of 1 and becomes fixed in the population. There is one more genetic process to talk about that isn't directly natural selection, but it is related to it. This is the phenomenon known as linkage disequilibrium. Once again, we're going to skip over all the complicated chemistry for now and just explore a broad oversimplification. Basically, genes exist in physical space on the chromosome. Due to this, some genes are literally physically closer to each other than others on the DNA strand. Alleles slotted into these gene loci that are in closer proximity are, for complex chemical reasons, more likely to be inherited together. For this reason, if a neutral allele lives down the block from an extremely beneficial allele that is experiencing intense natural selection in its favor, the neutral allele can ride on the coattails of the beneficial one and skyrocket in frequency as well, through no merit of its own. Truly, the neutral alleles in this scenario are the Nepo babies of the genetic world. And just like Nepo babies, some problematic behavior can be overlooked due to their close proximity to somebody in the spotlight. See, if there is a mild or even moderately detrimental allele next to a massively beneficial one, linkage can drag that negative allele to higher frequencies in the population, resulting in its detrimental traits becoming more common. The inverse can also be true, where a moderately beneficial allele next to the genetic equivalent of a train wreck can be completely selected against and removed from the population, despite its beneficial effects. So, those are the major ways that evolution can occur without any type of direct selection. These processes function mostly on random chance, whether it's the odds of a neutral allele being passed along to a new generation, how close they sit next to a more important allele, or even the odds of a brand new allele coming to exist through genetic mutation.
Is it time to talk about evolution through natural selection now?
That's right. Now that we've spoken about how evolution can occur without selection, it's time to dive deep into the process that does more than anything else to shape the form and function of life on Earth. Evolution through natural selection is very... looks like we're out of time today. I guess we'll have to explore natural selection next time.